opening to 0 without revealing its origin. Having this cryptography, it's quite straightforward to build a zero-coin-like functionality. The user can mint new coins as a Peterson commitment. He just generates a coin with serial number S and commits to it. And this coin, Peterson commitment, is published to the blockchain. When the user wants to spend it, he just has first reveal the coin serial number, and this reveal serial number will prevent the double spending attack, so the same coin cannot be spent twice. After revealing the serial number, the user just scans the set of all previously minted coins and homomorphically subtract this value from all commitments. This obviously results to a new set of commitments where one will be a commitment to 0. And the knowledge of this commitment can be proved with this one out of many proofs. This is the design of one out of many proof constructions. I don't want to dive into its mathematical details, just wanted to show how simple is it, and you see that the proof and verification procedures just fit in this one-page diagram. And Lelantus is leveraging this one out of many proof technologies to build a new protocol for anonymous and confidential transactions, which support fast page verification of transactions, enables to make direct anonymous payments, and as we will see, is also compatible with Mimblewimble and confidential transaction protocols, and potentially also with Ring-CD used in Monero. So let's go into more details. As our first goal is to get rid of fixed denominated coins and enable confidential transactions of arbitrary values, in our design, coins are represented as double-blinded commitments. We are using 3 independent generators like G, H1, H2, and each coin is associated with a unique serial number witness S, the coin value V, and the random blinding factor R. Next, we have to modify the original one-out-of-n construction to support this double-blinded commitment scheme. So this new scheme is just a protocol of knowledge that 1 out of n double-blinded commitments is opening to 0. Makes sense? So Lelantus supports 2 types of transactions. First one, mint transactions, enables to transfer base layer currency to shielded coins of arbitrary values and provide a proof that the sum of these output coins just is equal to the minted input amount. And also, no coin contains a negative value. In order to prove this, we have also to modify the bulletproof wrench-proof protocol to support double-blinded commitments. Next transaction, joint split, enables to merge, split, and redeem coins of arbitrary values without revealing the origins of inputs, and while enabling and while ensuring the confidentiality of both input and output coins. You see, we can make an anonymous spend with help of this one out of many proofs, but what is interesting here is this proofs, one out of many proofs, already contain all necessary information required to also generate a balance proof, to show that the transaction outputs sum up with the inputs without revealing the input's origins. This is the design we are using for one out of n proofs. Again, we will not go into all details. I will be happy to discuss it after the talk, but just want to highlight that proof transcripts contains 2 magic values here, ZV and ZR, which are kind of encoding the coin's blinding factors, V and R. So you don't reveal your secrets, but you have some encoding of that contained in the proof transcript. So let's imagine a joint split transactions which spends annual inputs and outputs a new coins. The overall transaction transcript will contain a separate one out of n proof per each spent input. And it also outputs n new coins. By zooming in into the formulas of these values, you can see that ZV encodes the coin value V, blinded by some random factors here, and the same is what ZR. And also the proof transcript contains some auxiliary information, these values Q, which are commitments of these blinding factors. Having this information, it's easy to generate the balance proof. As all this data is published on the blockchain, all network participants can just compute two values, A and B, in the following way. A is the product of all output coins, which will result to a new let's say, double-blinded commitment, which encodes the sum of all output coins. And then users can compute value B, just committing to the sum of ZV and ZR, and also using these elements QK to cancel the noise in these elements. This will result to a formula which encodes the input of all spent coins in the exponent of this first term. And it's easy to notice that when the transaction balance is preserved, then computing A over B, we will have these H1 terms cancelling each other. So the resulted A over B will just be represented with respect to generators G and H2. So in order to finalize the balance proof, the prover have only to generate a generalized Schnorr proof of correct representation of this value. Next, let's see how we enable direct anonymous payment through this protocol, or in other words, how the sender can create coins which can be spent only by the intended recipients. The original Lelantus design had some limited support of this functionality, which worked in the following way. Every time Alice wanted to send some coins to Bob, they engaged into Diffie-Hellman-like key exchange. So Bob published his public key, and Alice used that public key to generate a common shared secret here, which was hashed to generate the coin serial number we can say. And then when Bob wants to spend the coin, he just revealed this public key and used it to generate the coin serial number. And it also used the public key witness as the spending key. As Alice didn't know the witness, she couldn't spend the coin. This is good, but the bad thing was that Alice knows this public key, which generated public key, so he can trace the network for known serial numbers, and she can detect when the coin was spent. We want a scheme where only the recipient, Bob, will be able to recover this coin serial numbers. So with Sarah Notter from Monero Research Lab, we came to an efficient protocol enabling untraceable direct anonymous payments, which is still quite an intuitive design. Instead of engaging into a regular Diffie-Hellman key exchange process, Bob sends a new type of public key, we call it blinded public key, of the following form. It's of the form of G to the X blinded by extra factor. Alice can use this public key to mint the new coin by just generating a randomness Y and committing to the coin value with respect to the generators. Of course, Alice has also to provide a range proof, convincing that this coin doesn't contain a negative value, which can be done through standard range proof bulletproof protocol. You see that C is a regular Peterson commitment with respect to generators Q and H2, but it's also a double-blinded commitment with respect to three generators G, H1, and H2. The good thing is, in this scenario, Alice never learned any information about the G to the power XY. So Bob, the recipient, will be the only person knowing this secret. So Bob will be the only person who can spend it without being traced. This change required some modification into the original balance proof generation process, but it's still quite straightforward. We see each output coin now will be associated with the generators in the public key Q. So computing the value A, which is the product of all output coins, now will be represented with respect to these separate generators. And intuitively, in order to finalize the balance proof, the prover has to show the representation of A over B with respect to these generators, corresponding to output coins. Next, let's see how we enable fast batch verification of transactions, of one out of many proofs. The verification of these proofs are linear of size n. They boil down to big multi-exponentation of this form, where the generators, as you can see, for each transaction, the generators are transaction specific. Because the users, for each spended coin, the user just scans the anonymity set, like the set of all previously minted coins. And for each spent coin, he has to subtract the coin serial number from the corresponding commitments, which result to transaction-specific generators here. But the good thing is, in our design, these serial numbers are revealed in the spent transactions. So we can incorporate them into the verification equation and get to an equivalent equation where the generators in the big multi-exponentation are transaction agnostic. This will help to batch verification of many transactions together. With the well-known techniques of batch verification and simple math modifications, you will get to this formula, which enables to verify like a bunch of different transactions by still using one big multi-exponentation of size n. This will help to save n exponentation per each new spend. And based on our benchmarks, the average cost for each verification can be as low as 13 milliseconds for anonymity sets of size 16,000, and it can be as low as 45 milliseconds for bigger size of 65,000. Last thing I want to discuss is the hybrid scam of Lelantus and Wimble. Two privacy projects, Green and Beam, are using privacy protocol called Wimble, which is a very interesting protocol enabling confidential transaction and resulting to very compact blockchains. But it has a privacy issue where the transactions are actually, it doesn't break the linkability of transactions. And Beam came to a design of modifying Lelantus to fit into Wimble and enabling anonymous transactions. Let me just give high-level overview how it works. And the more detailed talk on this has been made by Beam's photographers and ZK Proof workshop yesterday, so you can find the video. So Wimble is an interactive protocol between the sender and the recipient, enabling to make confidential transactions. Each transaction is comprised of the input coins and output coins, which are represented through regular Peterson commitments, and it also contains some auxiliary data referred as transaction kernels, with Schnorr proofs, which show that the transaction is balanced, meaning the transaction fee plus the sum of output coins is equal to the spent inputs. The first important design fact of this hybrid scam is the fact that we can combine regular Peterson commitments and this shielded double-blinded commitments into a mixed confidential transaction, and still provide a generalized Schnorr proof that the transaction is balanced. The idea is, yeah, you can spend regular Peterson coins, but output double-blinded shielded coins. While still proving that the sum of output is equal to the sum of the inputs. This results to a new shielded pool on top of a UTXO set, and the user is able to spend coins anonymously from the shielded pool. For doing that, it just works in the following way. The user again reveals the coin serial number, which is GS, and then instead of providing one out of n proofs for double-blinded commitment, just to show that one of the coin will be commitment to 0, it also outputs a new Peterson commitment, a new coin, which encodes the same value but with another randomness. Next, the user can again scan the shielded pool and homomorphically subtract the product of the coin, serial number, and this new commitment from all minted coins. Obviously, one of the resulted commitments will be an opening to 0, which knowledge can be proved with standard one out of many proofs. This helps the user to just extract the regular Peterson commitment, regular coin, from the shielded pool. And this extracted commitment already can participate into mixed Wimble-Wimble transactions, which the output of which can again be shielded coins and can be added to the shielded. The same ideas can be used to combine Lelantus with confidential transaction design, that Wimble-Wimble. So let me conclude by showing the performance, comparing how Lelantus performance compares with other privacy technologies. You can see that the proof sizes and the performance is compatible with Monero, although we are able to support much larger anonymity sets, which will make the scheme resistant against flooding or transaction graph analysis attacks. Not surprised that it's hard to build zero cache performance, which comes with minimum proof sizes and blazingly fast verification. But unlike zero cache, we don't require any trusted setup. We are using only standard cryptographic assumptions. And what is more important, we are not employing any complex arithmetic circuits. So this is a design which is easy to implement, easy to test, easy to do cryptanalysis. And we believe that there are many ways that Lelantus can be significantly improved. An interesting open problem here remains to support staff addresses in the direct anonymous payment system. It will be very interesting to design efficient M out of N proofs and new cryptographic protocols which will help to prove that M, let's say M out of N commitment is opening to 0, and this will result to significant proof size optimization for transactions having more than one input. And we are now working to support multi-asset transfers and also enable auditability of transactions for enterprise use cases. So as we still have plenty of time, we'll be happy to answer questions. Thank you for your attention.
Just wanted to know how different is this from Grin and Beam, because they also use Wimble-Wimble, I believe.
Yes, they are using Wimble-Wimble.
Yeah.
And we discussed Wimble-Wimble is a totally different protocol.
Okay.
Which comes with some privacy drawbacks. For example, it doesn't really break the linkability of transactions. So we just discussed how this can be combined with Wimble-Wimble to solve the problem. Okay, no questions. Thanks so much.